First, I want to thank Sion and Mattel for their invitation. It's a great pleasure to talk about this recent project about this Lyapunov exponent of the stochastic heat equation with general initial data. So this is a joint work with Promit Ghosal, who will be a postdoc in MIT in the coming semester. And our paper is now on arXiv, so feel free to have a look. So our talk is organized as following. So first, we'll talk about some background about this stochastic heat equation and related things. And the second part will show the result and talk about some heuristic behind it. And the last part will talk more serious about our proof, like how to prove our result in a rigorous way. So what is stochastic heat equation, or SHE? It's the SPD given by the following form, with C to be the space-time white noise. So the solution to this SHE is well posed. You can either formulate it like in the sense of mild formulation or use the martingale problem. So as long as you start from any reasonable initial condition, for example, this initial condition does not grow too fast, then the solution exists and it's unique. And if you start from any positive initial condition, then the solution will remain to be positive at any time. Okay, so this is a result by Carl Mueller in 1991. So this stochastic heat equation has a very interesting connection to the KPZ equation, which is a very important SPDE introduced by Kardar-Parisi-Zhang in 1986, given by the following form. So it's a very nice model for the random interface growth. And the connection is given by this Hopf transform, which means if you look at the solution to the SHE here and you take the logarithm, then this H will solve the KPZ equation here. So in this talk, our result will be twofolded. On one hand, I will show you how to compute the Lyapunov exponent of the stochastic heat equation. So the Lyapunov exponent will be shown in the next slide about its meaning. And on the other hand, I will show you how to apply this computation to get a large deviation principle for the KPZ equation. So for the stochastic heat equation, actually we're interested in two kinds of initial data. The first kind of initial data corresponds to narrow wedge, which means we start our SPDE from a Dirac mass at 0. The second kind of initial data corresponds to this general initial data, which means we look at time 0, our initial data to be this exponential of f, where f is just some general measurable function, which can also be random. So it's actually a stochastic process. Think about f as a two-sided Brownian motion, for example. The reason here I set this initial data to be exponential of f instead of just f itself is due to this link to the KPZ equation. Because in this setting, if you take the logarithm of our ZF, then it will solve the KPZ equation starting from the initial data f. And also in this setting, our initial data is always positive because it's an exponential function. This guarantees the solution to our stochastic heat equation is always positive. Okay? So actually, in the narrow wedge case, the solution is always positive as well. Now we define something called the Lyapunov exponent. So we look at any positive real number p, and we define the piece Lyapunov exponent of the stochastic heat equation to be the following limit about the piece moment at time t. Okay? So if such limit exists, we say this gamma p is the piece Lyapunov exponent. And actually, as notation, we use this gamma narrow wedge and gamma f to denote the Lyapunov exponent of the stochastic heat equation starting from this narrow wedge or this general type of initial data, so this exponential of f. And so just want to emphasize, when you see this gamma f, I'm actually always looking at the stochastic heat equation starting from this exponential of f, okay, not f itself. Okay. So the Lyapunov exponent of the stochastic heat equation actually has a very interesting connection to the large deviation of the KPZ equation. So this was partially discovered by Sion and Li Ching-Tai last year for the narrow wedge case. So what is the connection? if we can show for some stochastic heat equation, starting from certain initial data, the Lyapunov exponent exists for every p greater than 0. Then, if you look at the following large deviation principle, so we say it's the upper tail large deviation principle for KPZ equation because we're looking at this probability of the solution becomes untypically big, and we look at how fast it decays, this probably decays as t goes to infinity. So we can show this large deviation principle with the rate function given by the right-hand side, which is the Legendre transform of this Lyapunov exponent. Okay, and this eta really corresponds to the typical value of our solution. So basically, when t becomes very big, our ht0 is approximately eta t. It's also like given by the information of the Lyapunov exponent. So this is something corresponds to the upper tail large deviation. So just want to mention this equality actually also holds for s smaller or equal to eta, but it's just the right-hand side becomes trivially 0. So if you're familiar with the large deviation principle, it's not very hard to see this connection. So this connection from the Lyapunov exponent to the large deviation principle. So in general, if you want to prove this convergence, in the language of large deviation principle, you prove an upper bound. So you look at the lim sup of the left-hand side, you show it's upper bounded by the rate function on the right-hand side. And on the other hand, you prove a lower bound. So here, let me just give you details for the upper bound proof. If you look at this probability, with h greater than st, you apply the Markov inequality. So it's upper bounded by this expectation. Then just notice that this exponential of h is the same as the solution to the stochastic heat equation. So this expectation really becomes the piece moment here. So by the way, I want to confirm you can see my mouse, right?
Yes, we can.
Okay, great. Then you take the logarithm and divide by t. So you take this limit. The right-hand side upper bound just becomes this term. And as you let t goes to infinity, by our definition of the Lyapunov exponent here, this part just goes to negative ps plus gamma p. And this inequality holds for any p greater than 0. Then you only need to take the infimum of the right-hand side over p, and it just becomes this object. So this corresponds to when you put the negative sign inside, it becomes an infimum. So this is basically the proof for the upper bound for this limit, and for the lower bound, it's also something standard in large deviation principle. You need to do some tilting, which corresponds to the change of measure. So I just omit the detail here, but it's something standard in large deviation principle. Okay, so I hope I have convinced you actually how to see the large deviation principle from the Lyapunov exponent. Okay. So for the Lyapunov exponent of stochastic heat equation, actually the computation goes back to the work of Bertini and Concrini, where they derive a Feynman-Kac formula for the integer moment of the SHE, and they try to do the computation for the integer moment, but unfortunately their computation has some mistake and only work for the second moment. So in 2015, Chen, he proved that if you look at f bounded and deterministic, so just remember our stochastic heat equation is starting from this exponential of f. So the initial data is really both upper and lower bounded and deterministic. In this case, he showed for positive integer p, the p's Lyapunov exponent to be this p cubed minus p over 24. Okay, so this number will appear a lot of time in the later talk. So to do this computation, actually, he looks very careful about this Feynman-Kac formula, and by some careful analysis on the Brownian local time, you get this quantity. On the other hand, if you look at the stochastic heat equation starting from narrow wedge initial condition, so for the integer moment, there is a contour integral formula, and by a residual calculus against this formula, Cohen and Ghosal in 2018, they proved the narrow wedge Lyapunov exponent is also this p cubed minus p over 24 for the integer p. And 1 year later, the result of Das and Tsai that I mentioned before, they proved the above equality actually holds for all p greater than 0. And by the connection that I showed in the previous slides, they obtain an upper tail large deviation principle for the KPZ equation starting from the narrow wedge initial condition. This is about some history. So the way they compute this Lyapunov exponent in the work of Das and Tsai for every p greater than 0, they utilize this exact formula for the stochastic heat equation starting from narrow wedge, which was obtained like first in the work of Amir Cohen and Kostel in 2011. So they use a very careful analysis against this formula to derive this identity for all p greater than 0. So actually, the initial motivation of our work is to study the stochastic heat equation starting from another important initial condition, which corresponds to the Brownian. So we start the solution from the exponential of two-sided Brownian motion. And in this case, actually, there's also an exact formula, which is obtained by the work of Borodin, Corin, Ferrari, and Vettel in 2014, where they use this exact formula to prove like the 1-point fluctuation of KPZ equation starting from Brownian initial condition have this background fluctuation. But for our purpose, actually, this formula is much more complicated than the one in Amir Cohen and Kostel. And it just does not tell us any useful information about the Lyapunov exponent for the Brownian initial data. So it turns out that we still managed to compute this Lyapunov exponent without using any exact formula. Okay. So this is actually the motivation of our work at the beginning. So let's just show this result. Actually, it's a special case of our result because finally we're able to do our computation of Lyapunov exponent for a wide class of initial data. But let's just see for the Brownian case. Imagine you look at the piece Lyapunov exponent of SHE starting from this exponential of two-sided Brownian motion. Then you get for every p greater than 0, it equals p cubed over 6 minus p over 24. So it's not p cubed over 24 like as we seen like in the slides before. There is a change. And as a result, you can obtain an upper tail large deviation with this rate function to be the Legendre transform of this p cubed over 6. So here I move this p over 24 here inside the drift. Okay. So this is our result about Brownian motion, and like in a few slides later, I will show you a result for and characterize the Lyapunov exponent for a wide class of F. But let's just first see some heuristic, like how we get this result, like for the Brownian initial data. Okay. So our idea actually starts from an identity, like in the work of Cohen and Hammond, where they look at the KPZ line ensemble. So if you look at the solution to the SHE starting from this general initial condition, then you can express it in terms of the narrow wedge solution times the initial data. So you have a convolution formula. It's something similar to, if you look at the solution to the heat equation, you can express it as a convolution of the heat kernel with your initial data. This is something similar, but I just want to warn you, this identity only holds at one point. So it does not hold time level. The reason is, like, in the process of deriving this, they use some space-time reversal of this narrow wedge solution. So this identity only holds for one point. And the narrow wedge solution and our initial data, so F is allowed to be random, they're coupled in a way so that they're independent. Okay. No, this only holds for one point, but it's enough for our purpose because we're trying to look at the piece moment of the left-hand side. Then it just becomes the piece moment of the right-hand side. Okay. Then the next step is very important. It's a heuristic step. Because what we want is to compute the Lyapunov exponent, which is defined as the log of the left-hand side and divide by t, let t goes to infinity. So basically, we're looking at some asymptotic. So like heuristically, we expect if you put the piece power here inside the integration, it should not affect your asymptotic. Though you will change the value of expectation, but in the level of asymptotic, it should not change it. So like in the rigorous proof, this step needs a lot of justification, as I will show you later, but let's just take it as the heuristic, okay, for now. So once this approximation has been established, then it's very nice because you can use Fubini theorem. You can put the expectation inside. And you can then use the independence of our coupling. So narrow wedge and initial data, they're independent. So you can break the expectation into a product. The next observation is actually, if you look at the narrow wedge solution to the KP's equation, it's stationary fixed time level if you add it by a problem. It's stationary in X. So this tells you if you take the exponential transform, you take the Hopf transform, then the stationarity is maintained for the stochastic heat equation. Then it allows you to express this piece moment in the integrand by the piece moment of the solution at Tn0 times the Gaussian density. So this parabola on the exponential is come from like this proposition. Okay? So it's not very hard to see this stationarity if you use the Feynman-Kalk formula for the stochastic heat equation and use some stationarity of the white noise. So this is something not very hard to show. But this observation just led us to express this piece moment in terms of the right-hand side. And because the piece moment of this, so this solution at T0, it does not depend on our X. So you can take this part outside the integral, right? Then you're allowed to express your piece moment as a product of the piece moment of the narrow wedge solution at T0 times the integration that only depends on the initial data. Okay, so I hope this step is clear. Then basically our work is done because what we want is just to take the log, divide by t, and let t goes to infinity. We want to figure out the limit. Then the task just breaks into two parts. We want to figure out the asymptotic of the first part and the asymptotic of the second part. But for the first part, we already know because it's the result of Dassen's high. They tell us this Lyapunov exponent is PQ minus P over 24. For the second part, because we know what is our Brownian motion, so what is our initial data, it's a Brownian motion, you can do the computation exactly. So you can compute this expectation because it's the exponential of a Gaussian, and you can also compute this Gaussian integral exactly to get this P cubed over 8 limit. Okay. Then the Lyapunov exponent of the Brownian of the stochastic heat equation starting from Brownian is nothing but the sum of these two parts. This narrow wedge part plus P cubed over 8. So it is P cubed over 6 minus P over 24. So I hope this heuristic makes sense about why it leads us to this result. Okay, so everything is clear for now. So I guess you might already wonder, it seems that our computation does not rely much on what is our initial data, because except for our last step, we have using like nowhere the property of our initial data. So actually, we should also be able to formulate a result for general kind of F using this heuristic. And for general kind of F, what do we need? The only thing we need is this limit converge for every p greater than 0. And then the Lyapunov exponent is just the narrow wedge part plus this limit. Okay. So we're going to impose some condition on our initial data. So heuristically, we only need this limit converge for every p greater than 0, and we can define some function g as the limit, okay? G, which map the positive real number to real number. But actually, for the rigorous proof, it turns out that we need something more, because remember in the heuristic step, we have like in one step, we put the piece power inside the integration, which is not totally being justified. So we need some condition imposed on the initial data, and it's formulated in these three conditions. So let me just explain them respectively. So starting from the third condition, we need some regularity over it. So we need this increment of our initial data to have the super exponential tail. So for example, you look at f to be Brownian as the previous case. This is of course satisfied because the Brownian has Gaussian tail, right? Which is super exponential. But this actually does not force our initial data to be continuous. For example, you can also take f to be any bounded initial data. Then this will also be satisfied. So this is something extra. We need some regularity for our proof. But for the first two conditions, it's really not a big difference to something we expect. Let's start from the first condition. If you look at the integration in our heuristic, you put this expectation on the exponential, then you will get e to the power log of this expectation. Then you look at your integrand, it's nothing but the exponential of this log minus px squared over 2t here. And if you're looking at the asymptotic of this object at t goes to infinity, actually so if you're familiar with something like Laplace method or steepest descent, the asymptotic of this kind of integration of an exponential is always governed by the maximum of your exponent. So basically it's governed by the maximum of this sup of your exponent. If the sup have the asymptotic of this gp times t as t goes to infinity, then this integration here, it should be roughly like this exponential of gp times t. And when you take the log limit, you will just get this same g. So this first condition is not really far from our heuristic. Just instead of control this integral, we need some control for the maximum of the exponent. So this is also designed for the proof. Okay? And the second condition is also not far from like what we expect, because what we have is we impose some perturbation like over the integrand. So instead of having p's power, we have this p times 1 minus epsilon, so some small perturbation. And we'll finally let the perturbation goes to 0. And instead of having this equality, we just need some upper bound. So roughly speaking, for many initial conditions that you're considering, if they satisfy our heuristic, then you will also satisfy these first two conditions, and vice versa. It's just like for the proof, for some technical issue in the proof, we really need our initial condition to be formulated in this way, okay? Instead of just something we expect. Okay, so these are our three conditions. And as long as our f satisfies some regularity, and basically you can just think of it satisfy this heuristic, then we know the Lyapunov exponent of the stochastic heat equation, starting from this exponential of f, is given by the narrow wedge Lyapunov exponent, which is p cubed minus p over 24, plus the g function. So what is the g function? The g function is basically defined by this first condition. Okay? So the first condition, it needs this limit exists for every p, but if such limit exists, then it defines a function g. And it's the same g function as in our result. Okay? And so we're able to compute the Lyapunov exponent. And as a consequence, we can get a large deviation principle for the upper tail of the KPZ equation starting from initial data f, with the rate function to be the Legendre transform of this gamma f here. So the reason you can see there's a difference, we do not have p cubed minus p, instead we just have p cubed, it's because we move again this p over 24 inside the drift here. Okay? And this zeta really corresponds to the typical value of this hf plus t over 24, as we mentioned before. And it can be computed from our function g. Okay. So everything clear about the result?
So why do you need the third condition, like the decay of the del?
Yeah. So the third condition really corresponds to when we look at the initial data at two positions not far from each other, we hope they're not going to be too far away. This is because, again, it corresponds to justify this approximation about we put the piece power inside. So imagine, like when we can put our piece power inside, like it corresponds to when your integrand does not change much as your x change a little bit. So we need certain kind of continuity, but not exactly. So this is the reason like why we need like this regularity, and you can also see it like in the proof later. We indeed need that. Okay.
Yeah.
Thanks for that. So this is a general result for our f. So let's just see for some concrete example, like as we see before for the Brownian motion, like how we can apply our results. So the first condition corresponds to our f to be sublinear. If f is a sublinear function in terms of x, and actually we don't really need our f to be deterministic. It just like simplifies some justification. But the key is we need our f to be sublinear. And we assume it satisfies some regularity condition, as we mentioned before. So in general, if f is some bounded initial condition, then these are all satisfied. And then we want to compute our g function. Like if you remember, the g function is defined by the first condition imposed on our initial condition. So if f, you take it to be the absolute value of x, then by a simple calculus, you look at this soup, it's a linear function in terms of t. But now if imagine our f is something sublinear, then you should expect this soup is also a sublinear function in terms of t. Then you take the limit, you just get the 0. So this is the definition for our g function. So for every p, our function should be 0. And the second line actually corresponds to verify the second condition, which you can also do a simple calculus to see the second condition also holds. So it tells us the g function in our theorem is just 0. So for any actually initial condition satisfy certain regularity and sublinear growth, you'll get the Lyapunov exponent to be the same as the narrow wedge case, which is this PQ minus P over 24. And as a consequence, you can get an upper tail large deviation principle. So I don't want to focus too much about verifying these conditions, but the importance is just if our f grows sublinearly, then it's just like the narrow wedge and the bounded initial data case. You just get this PQ minus P over 24. Okay. So the second example actually is similar to Brownian motion, but this time we add some linear drift over it. Okay. So actually, we consider two side different deterministic drift, A1, A2. And we want to verify our condition. So because we have a Brownian motion, then it definitely satisfies the regularity condition. And you only still need to compute the g function, actually. And because what we have is some Gaussian random variable for each x, we can do the computation exactly and get the g function to be the right-hand side, where a is based on drift. And this plus sign just means when p over 2 plus a is positive, you get, like you just get itself. And when the p over 2 plus a is negative, you get 0. And so you know the g function, we can also verify like these conditions all hold. Then it tells you for so if you look at the stochastic heat equation starting from Brownian initial data with different drift, the Lyapunov exponent is just the narrow wedge part plus this extra part. Okay. And actually, something interesting when you look at the large deviation principle, the rate function will depend on my A, which is the maximum of my drift. Okay. And when A is positive, you'll see the typical value of this HF plus T over 24 is around this A squared over 2 times T when T becomes big. And this is our rate function. But when this A becomes negative, so the typical value of this HF plus T over 24 just becomes 0. And you'll see a crossover in terms of rate function. When S is small, when S is close to 0, the rate function is the same, if you remember, as the narrow wedge case, or the previous example when our initial data have sublinear growth. But when S becomes something bigger, the leading coefficient just transfer from 4 square root of 2 over 3 to 2 square root of 2 over 3. Okay. So in particular, when you consider Brownian cases, A is just 0, and you get this negative 2 square root of 2 over 3 rate function. Okay. So this is 2 important examples for our general result. One is for the sublinear growth function, and the second is for the Brownian initial data with a certain drift. So before I go to the proof, like how to justify our heuristic, let me just do some summary and some comparison. I'm interested in this object, this HF, if you scale the time by 2, plus the drift and divide by its fluctuation. I'm interested in looking at the limit of it. And I'm also interested looking at the upper tail large deviation for this object if you replace this t to the negative 1/3 by t to the negative 1. So this is in the large deviation regime. I want to compare different results for 3 important initial conditions for my KPZ equation. The first one is the narrow wedge, and the second one is flat, which corresponds to my F is 0. The third is Brownian. So it is well known, actually, for the narrow wedge case, you'll have the limit law of this fluctuation to be tracy rhythm GUE. The flat is well believed, though I think it's not rigorously proved, to be GOE times some scalar, and the Brownian to be this F0, which is the backrange distribution. And if you look at the right tail of this limit law, you'll get the blue tail exponents. Okay. On the other hand, by the results of Das and Tsai, we know the upper tail large deviation for this quantity if you divide by t instead of cube root of t. And by our result, we know the case for flat and Brownian initial condition with the upper tail large deviation rate function given by the red number. So you can see it does not depend. Okay, so first, our upper tail large deviation rate function does depend on our initial data. So for example, you can see the Brownian case is different from 2 other cases. Second, no matter what kind of initial data you're looking at, the right tail of the limit law always coincide with the upper tail large deviation rate function. So this is actually something like well observed by the physicist. So this basically tells you the upper tail of the KPZ equation is very robust and it does not have any crossover happen. So if you're familiar with the lower tail, like you know, actually the lower tail have this crossover from tail exponent s cubed to s to the power 5 half. But for the upper tail, it's very robust. And this coefficient, they also match with the right tail of the limit. Okay. This is some summary of different initial conditions about the large deviation rate function. So now let's go to the rigorous proof. Remember, in our heuristic, what we want is to justify that we can put the piece power inside the integral. But for our proof, so this is always like something behind our proof, but to to do our proof, actually, we consider a slightly different approach. So we want to prove this limit to be the g function plus the narrow wedge Lyapunov exponent. So we prove a lower bound and upper bound respectively. And remember, we have imposed two conditions on our initial data f, so along with the regularity of f. So the first condition will be used to prove this lower bound, and the second condition will be used to prove the upper bound. So we'll start with the upper bound, and actually we'll again divide the proof for upper bound in two cases. One case is very simple, so so I will only use very elementary tool. Let me just present you first. Okay. So we want to show upper bound. So just recall, this upper bound corresponds to the limit is upper bounded by my Lyapunov exponent. I'm looking at the upper bound when p is greater than 1. And remember, we can write our ZF as the integration of the narrow wedge solution times the exponential of our initial, so times our initial data. So what we do is actually use Holder inequality. So this is a simple trick. We just multiply ourselves by a Gaussian density and divide it. This allows us to use the Holder inequality to break this integral into a product as upper bound. And Q is just something satisfy 1 over P plus 1 over Q equal 1. Then what we do is we look at the P's power of our ZF and take the expectation. Then this 1 over P just disappear, and we get something like this by compute. And this term really corresponds to the exact computation of this Gaussian integral. Then you can see actually we have the heuristic, because what we want is just we want to put the P's power inside the integration, which is exactly the right-hand side, except we have some extra term about which is some small perturbation, where this epsilon can be taken as small as possible. Then we just do the exact same thing as in our heuristic. We theorem put this expectation inside, and using the independence of the narrow wedge and our initial data, and also using this stationarity, we can get the upper bound as the right-hand side. So this is something really close to our heuristic, except we have this px squared, we have some perturbation of it. Okay. Then we're basically done, because we just take the logarithm, it's upper bounded by the right-hand side, and we divide by t, letting t goes to infinity. We're looking at the asymptotic for the right-hand side. For the first part, it just goes to 0, because it's log t divided by t limit. The second part will goes to our Lyapunov exponent of the narrow wedge, which is pq minus p over 24. And the third part, remember, this is our condition. So actually, at the beginning, you might wonder why we impose such weird perturbation. It's for the proof, actually, because when applying Holder, we'll have some perturbation over here. Actually, for the integrand, they're really close, except we have this p times 1 plus epsilon. You have p here. But it's natural to believe this integration can be upper bounded by the one in our condition, because here you increase the moment a little bit. So you can use Holder to get this upper bound. And actually, there's some detail, but I think it's convincible that you can show this limit is upper bounded by the GP on the right side. Okay, so I guess you might also wonder, why here I do not just set our condition to be p to the power f, exponential of pfx, but p times some perturbation, which match with here. It's because we also need to deal with the upper bound for p between 0 and 1. And you'll see, actually, we need, there's some perturbation at here. Okay. So this is basically the proof for p greater than 1. And what we use is just some Holder inequality to make our heuristic rigorous. Okay. So I hope it is clear for this case. Okay, so now let's go to the other case, which becomes much, I would say, more complicated. When you look at the upper bound when p is between 0 and 1, then cannot use Holder inequality because our p is more than 1. But you have some extra tool which corresponds to subadditivity. So it basically tells you when you look at this sum, like either finite or infinite of some non-negative thing, you can upper bound it by putting the piece power inside. So why this is useful for our case? Because when you look at this integration, you can write it as the summation of the integral from n to n plus 1, then you sum it over n, right? So you have actually the piece power of a summation. Then this additivity, put the piece power inside, and you get the summation of the piece power here. The reason we do this, now you only need to look at your integral like on a small interval. And the heuristic is following. If we can show the solution, the narrow wedge solution, at position x, when x is between n and n plus 1, does not go very far away from the solution at n. And then we can do this replacement. We just replace every x by n. Then this term in the integrand no longer depends on our x. You can take it outside the integration, and you can put the piece power on it. And then you can use the independence to break the expectation apart. So this is something what we do in our heuristic before. Then it really corresponds to justify that we can do this replacement. We need to compare the solution at x with the one at y when x and y, they are not far away from each other. For example, their distance is smaller than 1. Okay. And to justify this, we need some extra tool, actually from the work of Promit Ghosal and Hammond. What they look at is they compare the solution at x with the narrow wedge solution at 0. So this problem, you don't really need to worry about it. And they see, actually, this increment uniformly, like in some interval, you can see it as a constant. The reason is both upper tail and lower tail, they have some super exponential decay. This epsilon can be taken arbitrarily small. And also this super exponential tail is uniform in t. So this constant does not depend on t. So this allows us to compare the solution at x and 0 when x is not far away from 0. But you might wonder how to compare the solution at x and y when, for example, both x and y, they're far away from 0. So you can use the stationarity, actually. You can use the stationarity to move the solution at position x and y to the solution at x minus y and 0. Though you have some problem in your stationarity, but like it does not really matter. So this provides the tool for our heuristic. And to use this tool, so let me just show a simple but turned out to be very useful lemma. So imagine I have a stochastic process which have the uniform super exponential tail. Okay? You can think of this stochastic process yt as the process here, because it also depends on t, and you have the uniform super exponential tail. So uniform just means our bound does not depend on t. And then we want to compute the product of some x times this exponential of yt. Then the lemma tells you, you can just throw this yt away, replace it by a constant for the upper bound, and at the cost, you just increase the power of x a little bit. Epsilon can be arbitrarily small. And this constant, it does not depend on anything. Okay, it depends on my process yt, but it does not depend on x, actually. So the proof is very simple because y have uniform super exponential tail. So for every p, if you put it on the exponent, this term is uniformly upper bounded by a constant. Then apply the Holder inequality. You can just break the expectation apart. And for the second part, you can just replace it by a constant because it's uniformly upper bounded. So get the desired result. And also, when yt have, let's say, super exponential lower tail instead, you can get the reversed identity. Sorry, you can get the reversed inequality. Throw it out like constant and just replace the moment by the power 1 by 1 minus epsilon, some small perturbation. So why this tool is useful? Now, we have already split this piece moment in terms of the summation of integral over small interval. And we really want to justify in each interval, we can replace x by n. To do that, we consider this object, which corresponds to the sup of this increment over a small interval, so over this n to n plus 1. The reason here we have some extra term is to guarantee our Jn is stationarity. So you can just replace, if you look at the distribution of it, you can just replace n by 0. But this term, actually, it does not really matter, just used to guarantee the stationarity. If you replace n by 0, you will find it just corresponds to we're comparing our narrow wedge solution at x to the one at 0. So then we can use the result, like mentioned before, by Ghosal, by Cohen, Ghosal, and Hammond, and to show our distribution of J and T have super exponential tail, and it's also uniform in T. Then, to justify this heuristic by replacing x with n, just notice this Jn is the sup. So Jn is greater than the right-hand side for every x. Then you take the exponential, what you get is for every x inside this interval, you get it's upper bounded by the narrow wedge solution at Tn times this exponential of Jn. Okay. What you do is you replace the ztx here with the right-hand side. And the right-hand side no longer depends on x. You can factor outside the integral and put the piece power on it, then use the independence to break the expectation apart. Okay. Then again, you use the stationarity. You replace this n just by 0 at the cost, because this narrow wedge solution of stochastic heat equation is not totally stationary at the cost of you have some exponential of this parabola coming out. But can this replacement and factor out this parabola, you'll get this upper bound. A very important thing I need to mention or emphasize is this constant. First, it does not depend on our time. It does not depend on the time here because the tail is uniformly super exponential. Second, it does not depend on our n because we have used the stationarity. This c is just some universal constant. Maybe I should not say universal. It just depends on maybe the p here, but does not depend on time and n. All right. So we almost have the same thing as the heuristic at the beginning because we already put the piece power like in the narrow wedge part, and we split the expectation apart. So basically, just a brief summary, we first use the subadditivity to get this upper bound. Then for each term inside the summation, we have this upper bound. Then what we do is just we apply this upper bound to each in, then we factor out this common expectation, and we get the piece moment is upper bounded by the product of this A1t term times A2t term. So we need to upper bound A1t and A2t, but now it's not that hard because if you remember this J0t, you have super exponential tail. If it has super exponential upper tail, then by the useful lemma that we explained before, you can just throw it out if you want to upper bound it at the cost of you raise the power a little bit from p to p times 1 plus epsilon. And you really don't need to worry about the Lyapunov exponent of this part anymore, because it's just, you're looking at the p times 1 plus epsilon Lyapunov exponent. It's really close to p cubed minus p over 24 if you let epsilon goes to 0 finally. Okay. And for this part, okay, so at the beginning you have a summation, and here you have some integration. It's something similar. We want to put the piece power like inside to get something like this. Then we need to use some regularity over f. Remember, like our f have the increment to be super exponential. So if you have the super exponential thing, then like I think I have convinced you before, you can indeed put the piece power inside, do some continuous approximation, then you get something like this. And as the cost, you need to raise the power and decrease the power of p here a little bit by perturbation. But this is really something imposed in our condition. Here, then you just take the logarithm, divide by t, and letting t goes to infinity, and let the perturbation goes to 0. You'll get the upper bound here to be GP. So here you will get the upper bound to be the narrow wedge Lyapunov exponent, and you apply them respectively. You get the upper bound for like for the object we want to be is p cubed minus p over 24 plus GP. Okay. Is there any question? I hope this logic is clear enough. Okay, so now basically we have already settled for the upper bound for every p between 0 and infinity about this Lyapunov exponent to be smaller or equal to p cubed minus p over 24 plus GP. Now we move for the lower bound. Actually, the lower bound, will be something simpler, because we do not need to divide it into two cases. We only need to look at just for one case p greater than 0. And remember, our condition is imposed over this superior. The idea is we are interested in where this maximum is reached. Of course, okay, this maximum may be reached at multi-points, but let's just take one of them to be the XPT. Okay, so I think you have assumed this maximum may not be reached, but actually you can just assume this is true. It does not make a big difference. And then you plug in this XPT, what you get is something like this. So the heuristic is following. We expect, because the narrow wedge solution, you can just think of it as some exponential of parabola. And what you're doing is you're maximizing something over the exponent finally. So you should expect this integration, if you look at the piece power of it, the expectation, it should be localized around this XPT. And then we do a really wild lower bound. We just do the localization around this XPT inside a very small interval. And we have this lower bound, and our heuristic is as before. We just want to show, actually, we can do this replacement for every x inside this integration. We replace x by xpt. Then actually, if we can do this replacement, then everything becomes simple, because we can again use the trick. We can take the narrow wedge solution outside the integration and put the piece power on it and use the independence. So the idea is similar as before. We define something about their increment. So this O1 term actually comes from the parabola that appear in the stationarity of the narrow wedge solution. The reason we impose something like this is actually using stationarity of this narrow wedge solution, we can move the position we're looking at the beginning. We're looking at around xpt. We can move it to 0. And then we can use the result about this comparison of x and 0 to get this object have uniform super exponential lower tail. As the same trick as before, because kp is defined as the infimum, so for each kp, it's it's smaller or equal to the right-hand side for each x this interval. And if you take the exponential, you will get this lower bound. Then what we do, we replace the ztx by the inside. Then we can do the same thing. We can just like take it outside the integral and using the independence, get something like the right-hand side. So now we're trying to get the lower bound for this B1 term and the B2 term. But as before, like if you look at this KPT, we know it has super exponential lower tail. So to get the lower bound, you can just throw this term away, like replace it by a constant. And at the cost of you need to decrease the power a little bit from P to P minus epsilon. And then you can use the stationarity because we are not looking at the solution at 0, we're looking at XPT. You can use the relation to move it to 0 at the cost of you have this extra term from the problem. And for the second term, actually, okay, we use the regularity of f to justify we can put the piece power like inside the integration, and we can use Fubini to. Oh, okay, so it's again like we use the regularity. We just do this replacement by x. So from x to xpt. So and finally we just get like some expectation over f at this position. All right. Then, okay, we have the piece moment to be lower bounded by the product of these two terms, but these two terms, they're again lower bounded by something we want actually. You will see in the next slide. Then we take the logarithm, and what we have is this lower bound. So this lower bound has two parts. The constant term does not need to really matter because we have divided by t and let t goes to infinity. So the second part, actually, if you look at the red part, you divide by t and let t goes to infinity. This just goes to the Lyapunov exponent of the narrow wedge. And it will finally be p cubed minus p over 24 if you let epsilon goes to 0, because it's just a small perturbation. So for the second part, if you remember, like our condition imposed over this maximum, so this xp is where the maximizer is. It's not very far away from it. It's almost the same, except you have some small perturbation. So I hope like justifying this can be lower bounded by GP. I hope like intuitively this is convincible because they're really close to each other, and finally you can let epsilon goes to 0. Okay, so this tells you the lower bound of our Lyapunov exponent is also like bounded by the same object, is p cubed minus p over 24 plus GP. So we have both the upper bound and lower bound like for the same quantity. Then we just justify indeed our Lyapunov exponent is p cubed minus p over 24 plus GP. Okay. So I hope everything is clear. And so basically this is everything. Let's do a summary. So in this work, actually we compute the Lyapunov exponent of the stochastic heat equation starting from the general initial condition. And as a consequence, we obtain the upper tail large deviation for the corresponding KPZ equation. So our initial data includes, okay, actually sublinear kind of initial data and the Brownian motion with drift. These are two important examples. And the tool we start from is a convolution formula, which enables you to represent the solution starting from general initial data in terms of the narrow wedge. Then we use the property of narrow wedge. Basically, it's given by the three of them. First is the stationarity. Then we use the work of Das and Tsai about this Lyapunov exponent. And finally, we need some incremental bound of the narrow wedge and KPZ equation in the spatial variable. Okay. So maybe some future question. So first, you can see like it may be a bit strict that we impose the regularity over our initial data. So it's but it's like really needed for our proof. Though it's not being shown in the heuristic. So can the conditions be relaxed? Or more generally, here we're looking at function valued initial data. So can you look at the initial data starting from distribution, for example? And the second question is actually very hard. So we have looked at the upper tail for the KPZ equation starting from general initial data. So how about the lower tail? So the narrow wedge case, the lower tail large deviation has been proved first by Beach and Tsai, then by Kafasol-Calais using a different method. But for the general initial data, it is expected the rate function does not depend on the initial data. It's unlike the upper tail case. So actually, like if you use this convolution formula, it's not very hard, and to use our method, it's not very hard to get an upper bound for this lower tail. But for the lower bound, it's very, very hard because we do not have the connection to the moment in this case for the lower tail. And the third question, you can also look at, so here I look at the KPZ equation or stochastic heat equation on the full space. You can also look at them on the half space where you have this Newman boundary condition and you have this parameter A. So actually in the half space, there is a phase transition happen at this A equal to -1/2. When A is smaller than 1/2, the fluctuation is Gaussian. When A is greater than 1/2, -1/2, it's the GSE distribution. And here, like I look at A equals -1/2, and you start from narrow wedge, you can obtain an upper tail large deviation for the KPZ equation in this case. And the method to get is again, like you use the exact formula. Actually, there's a formula like for this case obtained by Shaolin-Parak, and you can do some careful analysis to get upper tail. But for other cases, the formula are totally, the formula are not like be rigorously proved. So it's interesting to study how the upper rate function, for example, you just look at the narrow wedge solution and you look at different A and to compare how this upper tail large deviation will change according to A. Okay, so these are some further questions, and thanks. Thanks for the attention.
Thank you, Yier, for the nice talk. So if anyone has questions, they can unmute themselves to ask. So I have a questions like in the case of lower bound.
Yeah.
Don't you need to quantify this XPT?
Yeah. Actually, you need some. Let me just go to lower bound.
Yeah.
Yeah. So you need some bound for this XPT. So for example, you need to show it. Yeah, it's actually it does not go too far. It's upper bounded by a constant times t. So that okay. Yeah. So that actually like this argument will work. But this is something technical, so I just do not show it in the proof.
So it's like you assume around an interval, it has maxima around.
So the thing is, I'm looking at the superior, and I assume the maximum can be reached. Actually, you don't really need to assume that. You only need to find some value so that it's close to the superior.
Mm-hmm.
And you can make it like an arbitrary close. You can take the limit, and this still works. And you just need to argue this XPT does not go too far away, like from zero.
Okay. So XPT is like linear in T.
Yeah, right.
I see.
So I have one question. In the half space case, so first of course, probably you said it, as the parameter A changes, like is anything expected about the large deviation?
Yeah. I remember in the paper of Pierre Ghosal and his co-author, there's something discussed for the case of A equal -1/2, and a equals 0 and a equal to infinity case. And they expect in -1/2 and 0 case, the large deviation function is the same, which is basically this 2/3 times x to the power 3/2. But when a becomes positive infinity, you'll just become 4/3 times x to the power 3/2. But actually, I just find something weird like before the talk, because like if you look at the phase transition, the fluctuation of this half-space solution is Gaussian when a is smaller than -1/2, and GSE when a is greater than -1/2. If you like believe this matching between the upper tail large deviation rate function with the right tail of the 1-point fluctuation limit, then you should expect the case for a equals 0 and a equals positive infinity, they should be the same because they're both in the GSE regime. So, but like in their paper, they like I did not look in the detail, but like in the introduction, they say for a equal to -1/2 and a equal to 0, like these two cases are the same, and for a equal to plus infinity, it's the rate function coefficient will be different. But I need to like look in more detail about that, like why they make this claim.
So you think that the connection between so in general, like large deviations and fluctuations, they belong to different type of scalings. But
yeah.
So you think that there is some connection?
Yeah, I mean, like if you see this, let me just go back to this table. If you look at the fourth space case, then the large deviation rate function is always matched to the right tail of the limit node. So it's natural to expect for the upper tail of half space case, such matching also works. So here, the large deviation means I divide this term by t instead of like t to the power 1/3. But then if the scaling match, then the tail and the rate function should also match. So this is something generally expected for the upper tail. But I think I really need to I really need to look more carefully about their paper, the paper of the Pierre Ghosal, like about their claim to make any further explanation.
And that's another question for the half space KPZ equation. Is there a relation between the Lyapunov exponent of the stochastic heat equation and the like
KPZ, the large deviation of KPZ,
and the large deviation? Yes. So.
Yeah. So in the half space, there's also the same connection. So the half space KPZ equation can also be defined by a half color transform. So instead, you just have a half space stochastic heat equation with certain like boundary condition. And in the case of a equal to -1/2 and narrow wedge initial condition, there's an exact formula for the Laplace transform of the half space stochastic heat equation. So you can do the exact computation to get the Lyapunov exponent. Yeah, so actually, like we compute the large deviation by computing the Lyapunov exponent of the half space stochastic heat equation.